Examine almost any solar array built in the last 50 years, and you will find the same foundational geometry. Our energy grid relies on flat, two-dimensional planes tilted toward the sky. While effective when the sun is directly overhead, this flat surface presents a severe physical limitation for the majority of the day. As the sun moves, it strikes the panel at increasingly oblique angles. This chart maps the relationship between the sun's angle and energy output. When light hits a flat surface from the side, the energy density per square inch plummets. This is known as cosine loss, a phenomenon that forces a choice between low efficiency or high-cost intervention. The standard industry response is a mechanical one. Panels are mounted to motorized tracking systems designed to physically rotate the arrays to follow the sun's path from east to west. This reliance on movement creates an engineering struggle. By forcing flat planes to move, developers introduce motor failures, high maintenance costs, and the need for perfectly graded, clear-cut land to accommodate the shifting machinery. A different approach discards mechanical tracking entirely. It replaces motorized rotation with static, three-dimensional geometry. This array is the conceptual power infrastructure developed by the Advanced Holographic Technology division of Techologram. Instead of rows of flat panels, the harvesting surface is distributed across isolated polyhedral nodes. By combining these complex structures with holographic optical elements, the design attempts to passively optimize light capture throughout the day without using a single moving part. This geometry is a deliberate, physics-based solution engineered to address the mechanical vulnerabilities inherent in traditional solar deployment. Analyzing a single node highlights the specific orientation of these steeply angled faces. In the early morning, this steep eastern face intercepts the low horizon sun at a near direct angle, bypassing the cosine loss that would otherwise affect a flat panel at dawn. As the sun reaches its zenith at solar moon, the upper apex and surrounding angled sides take over, capturing the overhead light. In the evening, the western faces become the primary collectors as the sun moves toward the horizon. Because the structure has multiple surfaces facing different directions, they activate in sequence. This results in a widened, sustained generation profile throughout the entire day. This comparison shows the difference in output. While a static flat panel produces a sharp, narrow peak at midday, the 3D node delivers a wide, consistent curve. By expanding the harvesting surface into the z-axis, the infrastructure achieves the steady yield of a mechanical tracker through purely passive means. This passive model stands in contrast to the heavy structural requirements of utility-scale mechanical trackers. Mechanical systems are prone to motor burnout, sensor degradation, and structural failure caused by wind shear against the wide panel surfaces. Tracking also imposes spatial limits. To prevent panels from casting shadows on each other during the morning and evening, rows must be spaced far apart, consuming massive amounts of land. The vertical orientation of these static modes reduces their ground footprint, allowing them to be placed closer together without self-shading. Removing the tracking hardware eliminates the maintenance burden and enables engineers to pack significantly more active solar generation into every acre of land. There is a complication with steep geometry. At extreme angles, light often reflects off the protective glass, rather than penetrating into the active silicon. The solution is found in the project's specialized use of holographic optical elements, or HOEs. In this context, holography is not about projecting images. It refers to nanostructured diffractive wave plates that control and bend light waves. These microscopic structures can aggressively redirect the path of a photon without the need for moving mirrors or lenses. This cross-section shows how the layers integrate. A specialized holographic microlayer sits directly above the photovoltaic silicon. When steep, off-angle light rays hit the surface, they encounter this diffractive layer. The wave crate captures these oblique rays and bends them 90 degrees downward, driving the light directly into the silicon below. This optical redirection neutralizes the reflectivity of the pyramid's extreme angles. The holography acts as a static lens, forcing diffuse light into an optimal trajectory and making the 3D polyhedral shape functional for energy harvesting. Combining these two distinct concepts, the physical macrogeometry and the diffractive microoptics, creates a truly unified system for continuous energy collection. The macrogeometry stabilizes the power curve throughout the day, while the microoptics maximize the yield from those steep harvesting angles. This creates a high-density energy node that lacks the vulnerabilities of traditional mechanical arrays. While flat silicon panels are approaching their theoretical efficiency limits, this design provides a new avenue for increasing total spatial yield. It shifts the burden of energy harvesting from mechanical engineering to optical physics. This shift enables a different approach to real-world deployment. Traditional solar farms require flat, graded topography to ensure trackers can move without obstruction. The static, vertical nature of these nodes allow them to be deployed on uneven or diverse terrain without destructive land grading. This flexibility permits power generation to be integrated directly into urban parks or industrial perimeters, rather than relying on cleared, distant fields. Technologram's development of this infrastructure marks a foundational pivot toward holistic spatial design. It represents a move away from simple panel efficiency toward a sophisticated use of available space. The evolution of renewable energy requires reimagining our physical relationship with the sun and moving beyond the limitations of the flat solar era. Securing dense energy in harsh climates lets us look past simple grid stabilization. It gives us the power to actively terraform barren regions. This creates a circular resource ecosystem. High-yield energy intrinsically drives large-scale water generation, which then provides the foundation for reliable food production. The immediate application is global computing. We can deploy hyperscale data centers completely off-grid, running solely on a surrounding perimeter of vertical holographic arrays. Those arrays self-generate the enormous volumes of water required for the server bank's evaporative cooling systems. Consequently, expanding global computing infrastructure is no longer physically constrained by municipal power limits or local freshwater shortages. Pushing higher solar efficiency out of smaller footprints directly lowers the cost per cubic meter for running advanced coastal desalination plants. In landlocked areas, the setup shifts to decentralized atmospheric water harvesting. Isolated holographic towers extract pure moisture from ambient humidity to supply remote zones. That water allows for controlled agriculture under agrivoltaic domes. Instead of competing with farmland, the solar array actually becomes the climate-controlled greenhouse roof. The holographic layer overhead blocks the scorching infrared heat while transmitting critical photosynthetically active radiation down to the plants below. The electricity generated by the roof powers its own internal irrigation systems, transforming completely barren land into a self-sustaining engine of water and food production. This integrated system acts as a resilient blueprint for power, space, and ecosystems. True sustainability means harmonizing with extreme environments through passive physics, rather than trying to fight them with fragile machinery. By solving the desert paradox, we secure a continuous, decentralized engine for regional resource independence. It guarantees energy, water, and food for future generations.